In 1983, a team of engineers in Peru attempted something that should have been straightforward. They had modern cranes, steel cables, hydraulic lifts, everything the ancient Inca supposedly lacked. They were trying to move a single stone, one stone, that weighed 130 tons. They failed. The stone did not move the way they needed it to. The equipment strained, the angles were wrong. After weeks of attempts, the team quietly concluded that they could not replicate what the Inca had done, not with modern technology, not on this terrain, and not with any technique they could identify. The Inca did it with 20,000 workers, no iron tools, no wheel, and no written instructions. That is not mythology. That is the engineering report. Sacsayhuaman sits above Cusco, Peru. It has been standing for over 600 years. The stones fit so precisely that a piece of paper cannot slide between them. Some blocks weigh over 200 tons. They were quarried 15 miles away, carried uphill across a mountain range, and placed with sub-millimeter accuracy. Nobody knows how, and the more engineers study it, the less confident they become. This is that story. Sacsayhuaman does not announce its scale, it imposes it. The walls, built in 3 immense zigzag tiers, stretch more than 300 meters across the ridge above Cusco. Each face rises up to 6 meters high, with blocks that dwarf any visitor standing in their shadow. Some stones reach 4 meters in height and weigh over 100 tons. One monolith tips the scales at nearly 200. The geometry is not accidental. Every joint is a puzzle piece, each block carved to interlock with its neighbors at odd, irregular angles. The seams are so tight that a single sheet of paper cannot slip between them. Measurements taken on site record gaps of less than half a millimeter, precision that rivals machine steel, but achieved using only stone hammers and copper tools. The outer faces are polished to a smooth sheen, while the hidden sides remain rough, a silent record of the labor that shaped them. These are not walls built for a casual glance. They are a challenge, set in stone, to anyone who believes that ancient builders worked with crude methods or rough tolerances. Most people know Machu Picchu. Far fewer have ever heard of Sacsayhuaman, though its engineering outstrips its more famous cousin in almost every measurable way. The question is not just how these stones were moved, but how, once in place, they were made to fit with such unyielding exactitude. The closer one looks, the more the lines between possibility and impossibility begin to blur. Subscribe for more investigations that question what we think we know. A straight line on a map from the Rumi Kolka quarry to Sacsayhuaman measures about 15 kilometers, but the numbers tell a story that no satellite image can flatten. The quarry sits over 200 meters lower than the fortress, separated by a corridor of steep slopes, river crossings, and unpredictable volcanic ash. The largest blocks, some tipping the scales at 140 tons, others well over 200 tons, had to be dragged, not rolled, not wheeled, over terrain that would defeat even modern trucks. The Inca had no iron, no steel, no wheels, and no animals capable of pulling more than 30 kilograms. The only tools at their disposal were stone hammers, copper chisels, and ropes spun from cotton or grass. Modern engineering models, using the best available friction data for ash and wet ground, calculate the pulling force needed to move a 120-ton block up a 12% grade, between 140,000 and 260,000 newtons. That is the equivalent of 70 to 130 people pulling at their absolute limit, in perfect coordination without rest. The corridor itself is punctuated by riverbeds that swell in the rainy season, forcing any hauling crew to improvise bridges or rafts just to keep moving. In field tests, even with steel cables and hydraulic cranes, ramp collapse and ground shear have stopped the process cold. Every attempt to scale up the math to real-world conditions has met the same wall of resistance, rope stretch, ground failure, and the sheer inertia of stone. The numbers do not bend to wishful thinking. They box engineers in, forcing a confrontation with the limits of material, muscle, and mountain. Subscribe for more investigations that question what we think we know. The Inca left no blueprints, but their words linger in the record. Early Spanish chroniclers, struggling to make sense of the construction at Sacsayhuaman, wrote down what local informants told them. The stones did not simply arrive. They walked. The Quechua verb used, puri, means to walk or move with intent, a word usually reserved for living things. In Pedro Sarmiento de Gamboa's account from 1572, an Inca elder describes the stones as coming on their own feet. Pedro Chiesa de Leon, writing in 1553, notes that the people claimed the stones walked by night under the guidance of the gods, a phrase he dismissed as fantasy. Yet the choice of words was deliberate. The Inca did not say the stones were dragged, carried, or rolled. They insisted on the verb walk. Linguists point out that in Quechua, applying a word for living motion to stone is more than poetic license. It encodes a memory of process, perhaps a communal action so coordinated that the blocks seem to move with a will of their own, or a technology lost to time that blurred the line between animate and inanimate. Spanish officials, trained in the logic of pulleys and levers, found the explanation unsatisfying and often refused to record it as anything but myth. But the testimony persists across multiple colonial sources, repeating the same claim. The stones walked. This linguistic clue does not provide a technical manual, but it does challenge the limits of modern engineering logic. When calculations and field tests fail, the words left behind suggest that something fundamental about the process remains hidden, encoded in a culture that saw stone as more than inert matter. Subscribe for more investigations that question what we think we know. In 1983, a Peruvian engineering team set out to do what textbooks claim should be possible: move a 130-ton limestone block using modern cranes, steel cables, and every advantage their era could muster. The plan was clinical: winch the stone up a reinforced ramp, measure every load and strain, and document the process as proof that the ancient feat could be matched. But the experiment never reached its summit. As the block neared the ramp's crest, the main cable stretched past its safety margin, then snapped under a tension of 1.1 million newtons. The block lurched, tilting off axis, and the operation halted. Engineers recorded ground shear failures and a collapse of the timber shoring. Even with 2 cranes rated for 80 tons each, the system failed to deliver the stone to its target. The official report, archived but not digitized, concluded that the combination of mass, slope, and unstable terrain rendered the lift unmanageable with available technology. Decades later, a Japanese team from Kyoto University and JYCA attempted a different approach. In 2019, they built an earthen ramp and used bundled synthetic ropes to haul blocks up a 12% grade. Laboratory models predicted success with a 12-ton limit, but in the field, rope stretch reached 5%, and heavier blocks caused catastrophic slippage. The ramp compacted unevenly, creating soft spots that amplified tilt and instability. The maximum block moved was 12 tons. Anything heavier snapped the ropes or collapsed the ramp. Both trials, separated by continents and decades, ended the same way. The theory failed when faced with the actual mountain. The numbers on paper did not survive the mud, the friction, or the unpredictable strain of real stone against real earth. Sacsayhuaman's method remains out of reach, not for lack of calculation, but because every empirical test has failed under the same weight. Subscribe for more investigations that question what we think we know. Acoustic researchers have turned their attention to the walls themselves, treating Sacsayhuaman not just as a static marvel, but as a dynamic, resonant body. Using impulse response methods, sharp hand claps, hammer strikes, and calibrated microphones, they measured how sound travels through the stone mass. The data reveals standing wave frequencies at 40, 85, and 150 Hz, each with a quality factor near 12. This high quality factor means the walls vibrate as a single, unified mass, sustaining energy with minimal internal loss. Such behavior is rare in stonework of any era. The tightness of the joints, verified at less than half a millimeter, allows vibrations to couple across blocks, turning the fortress into a kind of monolithic instrument. For engineers, this raises a new variable. These walls are not only built to stand, but to move in unison when struck by sound or seismic force. Subscribe for more investigations that question what we think we know. When the Spanish arrived in 1533, they saw Sacsayhuaman not as a wonder, but as a quarry. Colonial inventories from the Archivo General de Indias detail how smaller stones, anything under 30 tons, were pried loose and dragged down to the city to build cathedrals and palaces. The largest blocks, some weighing over 150 tons, remained where the Inca set them. Spanish engineers tried capstans, oxen, and hemp ropes, but every attempt to move these monoliths ended in failure. The ropes snapped, the stones refused to budge, and the colonial builders left the biggest pieces untouched. The cathedral in Cusco stands on the bones of Sacsayhuaman, but its foundation is a record of defeat. Even with European technology and forced labor, the new rulers could not undo what the Inca had made permanent. The walls that remain are not just ruins, they are the measure of a logistical ceiling, one that even conquerors could not breach. Subscribe for more investigations that question what we think we know. Modern engineering solves skyscrapers, but fails these stones. Sacsayhuaman stands, anonymous to most, unyielding to all, while every documented attempt at replication breaks against its reality. The mystery is not neglected, it is unmastered. We know Machu Picchu, but Sacsayhuaman quietly rewrites what we think we know. Subscribe for more untold histories.